you're in for a full day of fun. Those of you who plan to stay here the full day. Those of you who aren't planning to stay here the full day, at least you'll have a little bit of fun. This marks the culmination of the educational effort on our soon-to-be graduates from our engineering and our advanced manufacturing and our industrial supervision programs. They've worked hard for a number of years and have worked very hard this semester on their projects to come up with good designs, and they have good presentations for the faculty. The feedback forms that you'll write on each of the teams that you watch, those are in the back of the room. For your grading forms, you get one of those per student, and that's only for the faculty mentor who's doing the grading. I have those at the front of the room. I also have at the front of the room the forms for our clients to fill out, and I'll give those to the faculty members as well. And then we also have peer eval forms, and we'll have peer eval forms for a number of years because for some reason the peer eval setting was the same as the setting that I used to print off the other things. So we've got lots of peer eval forms, lots and lots of peer eval forms. Okay, without further ado, our first team, their project mentor, was Professor Kevin Nelson. Kevin, come on up, introduce your team. Or you can introduce them from down here.
Good morning and welcome. Our first presentation is done by the team of Mr. Ron Bordner and Alex Benedict, and what they have done is the implementation, installation, and deployment of a temperature control unit for our injection molding machine in the Applied Engineering Center. So without further delay, gentlemen, take it away.
Good morning. I'm Alex Benedict.
And I'm Ron Bordner.
And this is our design project for the temperature control unit on the USI's injection molding machine. We'd like to briefly acknowledge all the support we had from the faculty and our industrial liaison. I would like to thank Dr. Mitchell. He's the department chairman. Mr. Kevin Nelson, whom you know. He was our faculty advisor. We'd like to thank Donna Moore for all the paperwork help and keeping us on task. And a big shout out to Scott Titzer. He's the Vice President of Business Development at Infinity Plastics. And Mark Whitfield, who's a Senior Project Engineer there. They were very helpful with us in our project.
The objectives of our senior design project was to install a temperature control unit to an existing injection molding machine. We used the TempTech temperature control unit and was placed on our Negrabossi 8055 injection molding machine. The parameters of our project were to increase the runtime to 0.5 hours.
Just some background on the injection molding process to further understand our our project. The first step is plastification. It's where your stock is fed into the screw and the barrel and heated up. Following that, it's injected into the mold when it comes together. Material is packed into the mold and it's held under pressure. And it begins to cool where it forms up. Finally, the mold opens up and the part is ejected. The primary concern for our project was that there was no temperature control on the mold whatsoever. So after the machine was run continuously, the mold would heat to a level outside control for the part that it needed to be at. And this was resulting in a high rate of parts with deformation, and basically the machine just couldn't be used effectively and as a teaching implement or in any production sense.
The temperature control unit had some of its own requirements. It required 10 gallons per minute flow rate before it would even turn on. Required a 55 PSI or higher. It was powered by a 460 3-phase. It had some built-in safety devices within the unit itself. One was a water supply pressure switch, a motor overload, pressure relief valve, a high temp limiter, and fuse control circuit.
So when we went to tackle this project, there were some main considerations that we had. And the first one really was, we wanted to be able to isolate every part of the system for a variety of reasons. And to achieve that, we put shut-off valves on all our water lines. So from the from process, the to process, the source and the drain, we had a brass ball valve directly at it. And some of the advantages for that were ease of maintenance, and we wanted to be able to isolate any leaks or flaws in the system quickly with minimal water loss. And it's possible in the future that the temperature control unit that we have now will need to be upgraded or to take it down for maintenance. And these ball valves make it really easy to just isolate the system at any point that you need to.
The water lines were color-coded, both for teaching purposes and for safety. The blue being to process, which is going to be your colder water. The red from the process. This allowed, combined with our quick disconnects on the mold, give us the advantage of ease of maintenance, changing out the mold, and it also allowed for less fluid to be wasted or spilled during the change-out process.
Here you can see a basic flow diagram of the system that we designed. You can see the shut-off valves that we placed at the unit. You can see water comes in from the supply, circulates inside the machine. The water is either heated or cooled depending on the feedback that it's getting from the machine. The water flows through the mold, back out carrying heat, which is exchanged again at the machine, and then any extra water that's used to regulate this cycle is drained off.
This is our schematic of the flow throughout the mold. You can see the mold has holes drilled into it at different locations. This allows for the mold flow to be rerouted based on the insert into the mold, if it would require different cooling ranges at different points within it. And you can see that the flow comes in from the bottom, from the to process, circulates through and then back out, exchanging out our heat.
When we first started, we realized early on in the process that we needed to determine exactly what the mold temperature needed to be for it to be regulated at. And we determined that the type of plastic has a huge impact on this. Infinity offered us the use of their IR spectroscopic analysis, and they determined that the chemical composition of our plastic was polypropylene. We learned after the fact, too, that the USI Chemistry Department also has this capability with a spectroscopic analysis, so in the future, that's something that the university could do in-house. Like I said, the material we discovered, or that we confirmed that we had, was polypropylene. It's rugged and resistant, has a wide variety of applications in a lot of industries, from medical to automotive, toy making. A lot of stuff is made out of polypropylene. And that's because it's a fairly rugged material. It's resistant to solvents, bases, and acids. But the key piece of information that we gleaned from this analysis was that in order for proper part formation, the mold temperature needs to be within 70 and 120 degrees Fahrenheit. So that was a huge point in our project.
With the original setup, the mold or the machine operation time was limited to 20 minutes. This was due to not having a true understanding of how warm the mold temperature was getting, which was causing us a high failure rate, which you'll see by the green. Our red and blue is the limitations of the material based on the temperatures of 70 to 120 degrees. With this initial setup, we had a 76% failure rate with just a 20-minute run time.
So you can see here, we wanted to showcase some of the examples of the material deformation we were getting. In this first picture right here, we want to highlight this and that. This is a short shot or a short mold is what this is called. And it's when the plastic doesn't fully fill the mold before solidifying. And it's caused by a number of reasons, some of which are directly related to the temperature control, the viscosity of the plastic, die design and mold parameters, so the temperature of the mold that is being done. Some, avenues of investigation for this would be to increase the injection speed, the flow of plastic into the mold, and raising the temperature of the plastic could also assist with that.
Another failure that we noticed was a brittle failure, which you can see by the arrow up top and then also by the bottom. And this is caused from the stresses being placed on the pin within the mold, which makes that circle. And as it's being injected, the material is not completely fully formed and set up, and it's causing stresses on that point. Another area is the silver streaking. It's the white radial lines. It's caused by insufficient drying of the material. One of the possible things that we would have, even though polypropylene does not require any drying, our material sits in a plastic bag on a cement floor, so it will draw moisture over time. And not knowing how long those materials have been sitting there, possible corrections would be change our material storing methods.
Well, and even for the testing that we did, all our production runs we did with material that was already in the hopper, and it had been there for at least a semester, so we believe that there was probably some moisture that had accumulated in there during that time. This is our modified setup. As you can see, it's got the same upper and lower parameters of 70 to 120 degrees. The green line that you can see is the set point of 80 degrees that we set on the temperature controller, so that's the temperature of the water as it's being input. And to confirm that we were holding the mold stably and that the temperature wasn't rising over time, we also took some data on the temperature through our testing run, and we found less than 10 degrees of variation. So we believe that to be fairly indicative that the machine now has a greatly extended runtime, if not indefinite. Another big point of that was we took it from a 76% failure rate down to a 6%, so that's a drastic increase in efficiency. And all those deformations that we had in the second run when it was temperature controlled were at the very start of the cycle, so we believe that
We believe that with our changes being made and the failures coming just at the beginning of the cycle when the mold is really at its coldest point, that once you do your initial setup and preheat and pre-stages of running of the parts, those will even be eliminated by having the mold be brought up to temperature before you run your first shot. Again, our testing confirmed that the temperature control unit being implemented was successful for us. The mold temperature was maintained within operational limits. The previous runtime, again, of 20 minutes with a 76% failure rate was now increased to what was being an indefinite runtime with only a 6% failure rate, and the 6% only came within the first 3 cycles of our mold being ran.
We obviously had some complications as we went through this process. When we first assembled everything, we had some leaks at various points in the system. So we reconstructed it with a recommended plumber's compound as a sealant, and that we ran several hours of testing after that and didn't experience any leaks anywhere in the system. Also, this hole right here, which is an inlet for the fluid from process, the threads were damaged, so we re-tapped those and didn't have any problem with that afterwards. And also the motor on the temperature control unit spun incorrectly because it had been wired up wrong. And the man who did the installation wasn't able to test it when he actually did it, so we just did a work order and had him come out and he swapped the leads.
Our economic analysis, we used a hypothetical situation. And in this situation, we had some assumptions. We had a $3 gross profit per part being ran with a cycle time of 15 seconds. The total to implement this project, dollar-wise, was $2,406.80. That was bill of materials, installation from facilities and contractor equipment. And with those findings, we come up with a break-even point at 840 parts, which is a runtime of 210 minutes. This not only showed that it was a greatly needed investment, but it will easily pay for itself.
We also had some future recommendations for the university based on the success of our project. And the first one would be the acquisition of a material dryer. Polypropylene doesn't require drying, but many other plastics do. So if the university is going to expand the variety of parts that it produces, a material dryer will be the next piece of equipment that they need to invest in. Another thing is mold temperature sensors, or sensors that go anywhere in the temperature control system. The injection molding machine has the ability to display additional inputs, so it would be a relatively simple matter to install additional pieces of information gathering sensors and display it for the user. We would recommend new molds for the machine or new inserts. USI has the physical capability and the software capability at the AEC to potentially in the future create more of these inserts for a variety of parts. And we also recommend a safety cage. The utilities come directly out of the trench at the AEC next to the machine, and a simple guard over that would go a long ways towards preventing that from being damaged or a trip hazard or something of that nature.
At this time, any questions?
All right, questions?
Nice installation. I do have a couple questions. You mentioned that you went from a 76% to a 6% failure rate. How many parts did you run in 120 minutes?
Let's see, I don't have it right here, but the machine has
I mean, order of magnitude. Thousands?
15-second cycle time, so 300-400 parts.
Okay.
So a reasonable sample.
Okay, yeah. Is you a bunch of your, even from the original, a bunch of them kind of look like they were cold errors too. And you said, increasing the temperature of the plastic. Is there any temperature control on the plastic?
There is. The machine was set up previously by another project last semester, and they had an industry contact. You can set a variety of different temperatures at different positions inside the screws, so that's something that can totally be modified.
Okay. And then last question, you said you recommend new molds or a different mold, because it says how flexible is this? Would the molds have to be drilled with this chilling loop, or what needs to be implemented on that? Does this make all the future molds more complicated?
I think Ron might be a little better.
The mold itself is one unit. There's a plate that gets put inside of the mold. So basically what you're doing is you're redesigning that plate
So the part that you drilled to circulate through stays the same, no
Yes.
matter what mold? Okay.
Yes, that's the
that was
stationary
not- That was
piece.
not clear, got it.
And with the extra holes, which
It was
you
what
can
that-
see through the flow, based on different material and the new design
So that,
that you would put in,
that right there, the middle part
yes.
comes out and new one puts in and the
Yes.
cooling part.
And then you can also adjust your cooling as it would be required by what your design is when you go in, so that you get your proper cooling for that.
Did you do, this is another question, but did you do any sort of calculation of what your maximum amount of cooling would be? Do we have a total size of the mold that we would be able to pull heat away based on the machine that you've got and the flow rates that you have?
You mean the insert itself, or the overall mold?
No, we don't know the upper limits of what we could cool, so.
Okay.
A lot of the information we gathered was just empirical evidence. We did some calculations, but nothing as in-depth as to like a maximum amount of potential heat transfer.
Okay.
We know that the temperature control unit will operate up to 350 degrees and as low as 30 degrees. So you can pull a range of 380 degrees difference between the highest and your lowest point. So the unit
Yes,
also
but how quickly? That's, the question is how quickly?
that would depend on flow rate,
Right.
which you can adjust by your piping, increasing your hose size, increasing your pressure, and changing your loops around the mold itself.
Right.
To be able to add in more flow.
So that'd be something to investigate a little further.
There's a whole class of people actually here that could do a finite difference.
Other questions? All right, if we don't have any other questions, let's give them a hand.